Hello, everyone. Let's take a look at some concepts. In conditional probability, you have this probability triplet. For A and B belonging to sigma algebra F, the conditional probability of A given B is given by probability of A given B, probability of A intersection B by probability of event B, as long as probability of B is greater than 0. So there's no point in, let's say, given it's going to rain, what's the probability that the event is going to get canceled? So rain would be, let's say, probability of B, and probability of A is basically the occurrence of event. But if the underlying probability is 0, then it's sort of meaningless. And the way these things actually get computed is you look at probability of occurrence of A divided by the overall occurrence of all the other events. So there are like n events, and n of A is the number of occurrences of event A. So it's a fraction. It's like 2 by 6 or whatever, some fraction, wherein 2 by 6 is 1/3 is the occurrence incidence rate of event A, and the non-incidence rate, so A complement, is a 2/3, wherein other events are occurring. Now, given knowing that, if you have to compute, this is also called incidence rate in statistical terms. It's also called relative frequency. But given that, if you have to compute probability of A given B, you take the ratio of A intersection B, which is like number of events where A and B are occurring together, divided by the number of times the B occurs, right? The incidence rate of B. So that's how you compute in real terms if you are measuring what a conditional probability of A given B is in a given experiment. Given this to be the case, an interesting thing to note here as a consequence of this is if, let's say, this is a note, if A intersection B is a null set, then what happens to the conditional probability? Both ways. If A intersection B is a null set, those two probabilities end up becoming 0. Why is that? You look at the formula, right? There is no intersection between the two. If they're not intersecting, then the numerator of that formula, which is this term, is 0. Then obviously this whole thing becomes 0, right? Got the idea, right? So the thing to note here is that if intersection B is a null set, then conditional probability is 0. Now, where is this used? I mean, a typical example one can think of is a scenario where you're encoding something on a disk. In the olden days, people used to have disks, and people would encode something on the disk, and there would always be errors. So let's suppose this is the code that needed to be encoded, and for some reason, this is the code that ends up getting written on a disk. So this table that you see here below means if one was supposed to be written, this probability is the measure of, given one was supposed to be written, one was actually written. Given one was supposed to be written, 0 was written. So this was an error. So these two are essentially 1. And then given 0 was supposed to be written, 1 was written, which was an error. And then given 0 was supposed to be written, 0 was written. Let's take a look at what happens. What happens to the union bound, or at least some notion of union bound, when there is conditional probability being described? So we have a conditional probability term here, and then there is a summation of these probabilities given conditioned on event B occurring. Now, again, we also write the fact that AIs are disjoint, right? This is a very important condition. AIs are disjoint means AI and AJ are disjoint. It doesn't mean AI and B are disjoint. Okay. So that also means that if this was disjoint, then there's no meaning in this. The entire term becomes 0. That is not the case. What they're saying is all the individual AIs are all disjoint. Okay. That is very important to note here. Given this to be the case, how do you prove this? and you have intersection B. You basically extend writing using the formula and writing it. Now, the top term can be written like this. Why is that? How can we write it like this? What's the reason this is possible? So we had this term and we converted that into this term. So what it means is, so whenever you're intersecting, the union of intersection of AIs with B is equivalent to union of just the intersection terms, because we are only measuring intersection terms, because as given in this initial condition, write it in white, because AI intersection B are disjoint. These terms are disjoint. And that is possible because AIs are disjoint. This is possible, as a result of which this was possible, as a result of which we were able to write this term. Now, given this to be the case, we can now write it as, we can get the summation term. How? Since the numerator is a disjoint set, and we know disjoint union of sets can be written as probability of I'm sorry, which is equivalent to summation, and then we have proven what was supposed to be proven. You got the idea, right? So the key thing here is to understand how you apply these two conditions and what's the meaning of individual AIs being disjoint, and that leads to this condition. And because this is true, individual intersection of AIs with Bs are also disjoint. Because of that, this is true. Because of that, this is true. And this becomes the definition of the final term. Okay, so let's take a look at two events, A and B. This is the definition. If two events A and B are independent, if probability of A given B is equal to probability of A. So if they're independent, so the fact that you're conditioning on an independent event has no relevance. As a result, this becomes, it's equivalent to not conditioning on anything at all, right? Now, if the same thing is true, if these are all consequences of independence term. So, so given this to be the case, if two events are independent, the intersection of these two events is a product of their individual probabilities. So we write this formally. The events in A1, A2, AN are statistically independent if for any set S that belongs to natural numbers, we have probability of intersection of all these events equal to, this is the product term. By the way, if you're not familiar with this whole thing, this beast, it means product of probabilities. Okay. So if you think about it this way, so next time you think of individual, whenever you have independent events, you can just multiply the probabilities. Okay, that's the idea. And that's the second consequence. And the first consequence is, if you're conditioning one event on the other, and if these two events are independent, you might not as well take into account the underlying conditioned probability. You can just write P of A given B is equal to P of A. So now we come to random variable. Random variable, this is an interesting name because it's neither random nor variable. It's just a function that maps the entire sample space, which is the collection of all the outcomes of a given experiment, to a real line. So that real line, we can extract a number, probability number. Now we write the definition like this. A random variable is a map X from omega to R such that omega belongs to omega. X omega is a number less than A. So that the entire thing is part of sigma algebra for all A belongs to R. So as long as this X of omega, which is a number, is less than A, this is a random variable. Okay. Now let's check as to what are the values A can take. Now here, in this specific example, like you have an experiment wherein you have heads or tails, the coin toss. The x of h is 1 and x of t is 0. Now again, we write the fact that here um, a is equal to infinity, right? This a term, that is condition. So as long as x of omega is less than infinity, so we check that. So x of h is 1, is less than or equal to infinity. As a result, this is a valid outcome. Now x of t is equal to 0, is less than infinity. As a result, this is also a valid outcome. As a result, the entire sample space is omega. Okay. Now let's change a values to be negative, negative infinity. Now, given that to be the case, omega belongs to omega, x of omega is less than minus infinity. Now let's check that. X of h is equal to 1, is less than or equal to minus infinity, which is not the case, as a result of which you don't have anything in the sample space. Now let's check the second one. X of t is equal to 0, is less than infinity. This is also wrong, as a result of which the entire sample space is just null set. Now let's take the a value to be half. Now omega belongs to omega. X omega is less than or equal to infinity. Now we check each one of the outcomes. X of h is equal to 1. Is it less than or equal to half? That's not the case. So there is no outcome is not added to the sample space. Now let's take the second one. X of t is equal to 0, which is less than or equal to half, which satisfies this condition, as a result of which this is the sample space, right? So you have to check every single time. Now, you remember this scenario wherein we had a disk when we rotated, and we explained this previously. So whenever you have a disk and then the sample space of a disk, and the experiment is you take some point here, you rotate the disk. Wherever the disk stopped, you see the difference between where the disk stopped to where it initiated. That difference is theta. Now, my question is, if we rotate this, what are the chances if we run this experiment, the probability of omega being 3 pi by 4? The probability was 0 because it's uncountable. We looked at this previously, right? But if we have omega equal to a range of angles, 3 pi by 4 to pi, that would definitely be a positive number, right? Imagine, okay, this is the initial point. You rotate this disk, and at some point it stops. The question is, what are the possibilities of at the end of the experiment it stops in between 3 pi by 4 to pi? The chances are very high, right? It's not definitely 0. So that's the point I'm trying to communicate. So now you map that idea of random experiment and outcomes and random experiment outcomes trial onto notions, onto experiments that you see on a daily basis, recording speech, taking a photograph. And in each one of these cases, we are compares measures of sets. We're comparing a couple of sets. It can be sets on a real line. So these are like two different sets. We'll be making a comparison between these two sets. And then from that, we are making the assessment that this set is longer or higher in value compared to this set. So, and this objective of making these comparison is facilitated by the tools of probability theory, which borrows from tools of measure theory, which we have dealt with passingly, which will make it a little more precise here. Not with too much detail, but bare minimum that is required to solve some of the problems that we encounter in AI ML subject. So the basic objective is this notion of measure helps us in comparing two sets of interest. And the way we do that is we end up having a measure on each one of the sets. And then we compare these measures. Okay. So the A is an event, and then it maps some set to a real line, and that eventually is the measure. And And if it is two-dimensional, this will become like a this is, as I previously told, probability has an interesting analogy in terms of the area or the volume of anything, right? Probability of anything is like, measuring the area. So if it is two-dimensional, then the measure of subsets on R2 is the area measure, which is something that we have seen. So in terms of Lebesgue measure, people, whenever you think of measure, the generalized notion of a measure is Lebesgue measure. The Lebesgue measure is non-negative, because in real world, there is no point. If you say my mobile phone is 5 inches longer, 5 inches in length, it makes sense. There is no meaning in saying my mobile phone is minus 5 inches. So all notions of measure that we see on a daily basis are positive or non-negative. The measure of a null set is zero. And let's say the disjoint union, again, this notion of disjoint union has come again. This disjoint union of two sets, disjoint meaning the intersection is a null set. The disjoint union of two sets is the sum of individual probabilities, which we have seen as a result of union bound, which we have introduced as a lemma previously. So sample space is the collection of all possible outcomes of a random experiment or a random trial. This is something that we've seen as well. All these are represented in terms of probability triplet, where the omega, this is capital omega, 2 to the power of omega, and p constitutes a probability triplet. Omega represents set of all outcomes. 2 omega a set of all subsets of this sigma algebra. All these three are part of sigma algebra, which is F. Okay, something that you can probably remember. So you're defining a probability measure on A, which represents the event on sigma algebra F. Okay, and then because the event A is a subset of sigma algebra, we can have probability, we can compute, or we can instantiate probability of that event to belong to a real line, which is a closed set from 0 to 1. Probability measure can be interpreted as uncertainty associated with it. Yeah, this notion is very effective. Whenever you think of quantifying uncertainty, probability tools come in handy. And length and areas, length if it is R, areas if it is R2, we represent probability on capital omega, set of all outcomes. Always remember this as set of all outcomes. So Lebesgue measure is the notion of length, right? And the probability measure is the notion of uncertainty associated with a particular subset of sample space. Yeah, these are terminologies that you have to get used to, so that next time whenever I say probability measure, we're talking about uncertainty associated with a particular subset of sample space. Then you define a function omega to RD. Okay, this is a very interesting function. We can probably guess what this is. This is a random variable. So there's a function which is a deterministic function which maps all elements of sample space to a d-dimensional real space. And then, this is one example. This is another example. And this is telling you why probability triplet is a special case of Lebesgue measure. This is telling you that probability triplet is a special case of Lebesgue measure, right? Probability measure P. Oh, this is wrong. This has to be, now it's correct. So probability measure, this is a set of all outcomes, and this is set of all outcomes. This is set of all subsets of omega. And if it is, let's say the probability measure is equivalent to a notion of length. This is Borel sigma algebra. You don't have to get into the details. R is the overall set which constitutes all the subsets. We never work with another interesting point to note is that we never actually work with all elements of sample space. We are basically using surrogates of these sample spaces, which we observe in real life, which is data. These surrogates is what you see in data, and these data as samples is random variable. The function that maps elements of sample space to d-dimensional real number is called random variable. It's neither random nor variable. It's a deterministic function. images are elements of range space. So in real life, we are only looking at elements of the sample space, which are surrogated by actual data or actual samples. So we don't actually deal with the population metric at all. We only deal with samples, which are like surrogates. Think of it as universal copy of something, and we take the local copy. Sample space will give you more information about the underlying random experiment being conducted. Again, this is repetition again. Every element is a range space of, okay, yeah, every element of this is a range space of the random variable, which is true. And we'll take a look at some other topics some other time. Thank you.